Sounds good.
Berkeley, 10 minutes late, but
yeah, they also had Michigan time. They got rid of it.
Get rid of it? Oh, that's too bad.
Much better.
You want to be on time.
Well, I just want to know whether the thing starts at like 11 o'clock or 11:10.
I see. Yeah.
But there's no pen time.
A couple of minutes late.
Couple of minutes. Yeah,
It's
it's normal. How are things for you?
Good. Busy, but yeah, ICC just finished. I was at Berkeley retreat, just came back.
Oh, nice.
Yeah. Did you go to this retreat before? The bear?
Yeah, the bear thing. The bear, like,
yeah,
it's
fun.
like Trevor.
Yeah.
Trevor's got everyone like.
Yeah.
It's like next.
Yeah. Well, fortunately this year he's not running, so it's more free.
Oh, I see. Oh no, it was not. Hopefully not Alyosha running it. That would be, if you do it at the last minute.
Yeah, Jay was there, so we played the charade.
Oh my gosh.
Yeah.
Of course.
Yeah, it was pretty funny.
Yeah, charades is charades Big J.
Yeah, one word. Somebody, I don't even know. It's a very long name for poetry, and the student didn't even know what it is. Maybe Aaron said, "Oh, it's a poetry." The guy is like, "Don't know. One word. Don't know."
Yep.
And you change your one word, guessed it. I guess you can look for the word that's.
I like watching. I played charades with him and his wife once. Oh my god, they're like it's competitive charades.
Yeah.
And like Jitendra starts spelling things out, and she's the only person who can tell Jitendra no.
Yeah.
She's like, that's not. You can't do this.
Good. All right.
By the way, so they're recording this in principle.
Right.
Do I need to do a microphone or anything? I tend to talk loud enough that everyone.
I think that you had to.
Okay.
I don't know what happens. Probably this enough.
I can try this.
Yeah. So usually somebody's.
I recorded my lecture once and I forgot to put this on. Great to see you. Thanks so much for the invite.
You put that button.
Yeah. I told students in my class, I was like, open
up maybe.
I think there's a sign.
Here.
Oh yeah. Oh, there we go.
Okay. All right.
I was like, I forgot to turn on the microphone. But then I realized I talked loud enough that the back one picked it up.
Yeah.
Cool. All right, so let's start today's seminar. So it's a great pleasure for me to introduce Dave Fouhey to PAN. It's probably the first time for Dave to come here. Yes. Yeah. David is a new faculty at the University of Michigan. So David said, don't ask him about footballs or games yet. You just get used to it. David was before that at Berkeley for postdoc, with Jitendra and Alyosha at Rose. David actually is a product of the CMU. Finished his PhD with Bina, Gupta, and Marshall at CMU. So very rounded education. Dave is really a fun guy, always out there doing new things. So he started with 3D perception from single image. And they're looking at how to infer the affordance of actions and geometry on a single image. So I understood what people said. A lot of fun problems and very courageously move into those topics. And at Berkeley, I guess he worked on many things 3Ds as well as navigation in 3D spaces. And David is the first one who introduced me to vlog, looking at the vlogs of people doing fun things in the wild. So generally just a lot of fun topics. But today David is going to talk about how to understand places and how to do things. Welcome to that. Thank you so much for the very kind introduction. It's really great being here, and I'm really looking forward to meeting a lot of you this afternoon. So I like to begin my talks with actually a picture. And so here we have an image which, unless you've seen my job talk, you haven't seen this one before. I'm going to eventually have to get another picture. But it's certainly a place that none of you have ever been to. And despite the fact that you've never actually been there, you actually have a very good idea of what's going on in the scene. And I think it's worth appreciating how much your brain understands. And so to illustrate this, just to have a concrete demonstration, let's imagine that in the next minute, the man behind the counter gets milk from the fridge. I want each of you to think about what would have to happen for this to take place. So just think about this for just like 10 seconds.
So hopefully all of you can do this, like a child can do this, a dog or a cat could understand the consequences of this. But let's just go through it together. And so we have the man behind the counter, we have the fridge in the back of the kitchen, and the man is going to have to walk over to the back of the kitchen in order to do this. And when he gets there, he's going to have to go to the refrigerator, he's going to have to reach out and open it and pull the refrigerator open. And this is an incredibly boring way to start a talk. And I hope this is the most boring hypothetical scenario you've been asked to think about in a while. But it's actually an amazing ability because you're all able to understand like how you would do things in this kitchen, even though you've never been there. And the reason why it's amazing is that this kitchen actually doesn't contain any of the information that all of you would agree is actually in the kitchen. So this picture, if you look at it, is just a grid of intensity values. And so this 2D grid of intensity values of a place you've never been to, you're able to take this and convert it into some sort of representation of the world that lets you reason about something which actually didn't even happen in a place that you've never actually been to. And so this sort of is an amazing ability of humans to understand scenes from an image and to sort of be able to imagine how you would interact with the place, how you would move around in the place, and to do so without having actually been physically present there, and just going from one single image. And so the goal of my research more broadly is to sort of get computers to have the same level of understanding of the sort of physical properties of scenes in terms of what can I do in them and how can I move around in it. And so if you're not in computer vision, the good news of computer vision is that a lot of stuff is working. And many of these things that you might read about in the New York Times are things like we can name things in scenes. So now we have systems where if this image came from Flickr and we have data that looks kind of like it, we can expect that we would get some reasonable outputs about where people are, where the oven is, where the refrigerator is, so on and so forth. We can put bounding boxes around things. And these things actually work fairly well and fairly robustly. Of course, assuming that your training set looks like the images you're evaluating on. The unfortunately not so good news is that the sort of understanding that we're able to get from computers these days is actually not enough. So if I just look at sort of where everything is in the scene, in terms of what sort of a state-of-the-art system would give us, you can see there's a whole collection of boxes of where people are, where the refrigerator is. But if I ask basic questions that you could just answer, like even a dog or a cat could answer, like where's the man behind the counter? Or like where can I walk in the scene? These things are totally inaccessible. And so the goal of my research is to really deal with the stuff that's not being covered by sort of the dominant focus these days in computer vision, which is naming things. And it's really focusing on the physical properties of scenes. And in particular, I'm going to talk about two sort of problems that I think are really important that I'm really excited about. And the idea is understanding how to get places. And so if I look at this scene, even though I am not physically present there, just from the visual input, I understand that I could walk around the man, walk behind the counter if I want to get to the refrigerator. And so I'm going to talk today a little bit about how you can do this sort of navigation tasks visually. So really just taking images and trying to figure out how do I navigate from one place to another. And I'm going to talk about a very specific problem. But this problem of learned navigation is, I think, something which is quite interesting. And of course, at a place like Penn, which has such a strong robotics program, I want to point out from the start that it's complementary to a lot of the systems that people have been developing. And I think there's a lot of room to figure out how these two connect. The other thing I want to talk about is understanding how to do things. And by doing things, I mean that if I say like an object detection system can tell you that this is a refrigerator, we have to be careful not to give these systems too much credit. The system, all that it's doing is it's a neural network that has been trained to take in part of the image, and it can say, okay, is it object category number 1? No, doesn't look like that. Is it object category number 2? No, doesn't look like that. And then you get to object category number 73 in this COCO data set that people use, and yes, it is object category number 73. And so associated with object category number 73 is a text string refrigerator. But basic questions like open or close, or how do I open this, or how do I actually interact with this world, just like the systems don't understand any of this. They have no hope of understanding it. And so in order to understand how to interact with stuff, or how to do things like make a cup of coffee, cut toast, open and close drawers, we have to observe the world changing state. And specifically, I think if we're going to have systems that learn about how the world works, and I hope we do, we have to have the data which lets us learn about how the world works by simply observing people doing things. And so I'm going to talk today about sort of how you get the data and a specific type of data that I'm now very interested in, which sort of comes with its own labels. And so today I'm going to talk about navigating from images. And specifically, I'm going to talk about the task of robustly following path demonstrations. And I'll tell you what I mean by that in a second. And the other thing I'm going to talk about is learning from observing humans interacting with the world. And specifically, I think the main challenge here is how do you get the data for this? Because the learning systems that we care about, they depend a lot on the data that we feed them. And we can either label the entire world, or we can sort of try to collect this all by hand, or we can find more scalable ways. And I think a lot of the interesting stuff is in how do you actually get the right data to learn about how the world works. So this is what I'm talking about, but I wanted to advertise what I'm not talking about. And specifically, as Janvo mentioned, I started and did most of my work in the area of taking a single 2D image and producing some sort of 3D representation of the scene. Now, this is, of course, an under-constrained problem. And so there's some degree of either, there's learning, there's constraints, there's lots of things to play with in this area. And there's also the big question of what do you actually mean by 3D? And this ends up being actually a very difficult question to answer and a very fun area to work in because simply the answers aren't very satisfactory. And so just as an advertisement, I'm just going to show you briefly one output that the system produces. And if we're meeting later today, I'd be very happy to talk about this as well. And so you could take a single input image. So this is a 2D image. This one's synthetic, but we can also get this to run on real images, of course, less accurately. You take this input image, and you can produce an output representation in terms of voxels. And so if you haven't seen a voxel before, you can think of this, okay, if you're under, I guess, 25, you can think of this as making the Minecraft version of a scene from a single 2D image. If you're over 25, then think of this as Legos. And so you're trying to produce a Lego version of the scene from a single 2D image, and so you can produce a sort of 3D representation. And you can see there's like a couch and a table, and of course it's not accurate enough to actually put this on a robot, but this is, again, an extremely difficult problem. And what I think is exciting about work these days is that stuff is starting to work a bit better, so we can actually now rotate the scene from another view, and it doesn't look horrible. So obviously, if you start looking at these, you can see that there are lots of mistakes. So the chair is not exactly a chair you want to sit on, but it's an area where we're making lots and lots of progress, and there's lots of fun stuff to be done. And so basically, we can take 2D images and produce 3D representations. And this is, again, by no means solved, but I think this is a very interesting and challenging problem area where we're making a lot of progress. And the big question is actually, I think, how do we represent things? And so one of the things I've been working on is questions about how do you actually represent the 3D that you can see in a 2D image. If I give you a mesh, there are some obvious answers, like if I actually have the 3D mesh. But if I have the 2D image, there's some fundamental ambiguities. And so those don't necessarily go away. And so the big question is, how do you represent this 3D structure? Like, for example, knowing that the bowl on the table is actually resting directly on top of the table, and it's not floating in midair. And so how do you represent these sort of joint uncertainties of all the objects? And so this is one of the big challenges, I think, in 3D. And this is actually why I got interested in navigation in the first place. And the reason why I got interested in navigation is I wanted to address the question of, basically, if I give you a large 3D space and you have partial observations, how do you represent that? So before I joined Michigan, I spent the semester in Paris, very nice. And you have this very large city, which you don't walk down all the streets. And if I want to learn about how to walk through Paris, and this is a big, large 3D space, the first thing I do when I move to Paris is I don't say, okay, I'm going to do this like Google does, and I'm going to sit down and I'm going to start mapping. I'm just going to walk down every single street with a Velodyne on my head. Instead, I just go about my daily business, and after a few weeks, I have a pretty good idea of how to navigate from one place to the other, even though there are certain parts of Paris where you can get hopelessly lost because the streets basically are not sort of orthogonal. I grew up in New York, so I'm used to streets that are orthogonal. And so somehow you have this ability to navigate in spaces that you have partial observations of and make inferences. And so I thought this is actually a very, very interesting question. Sort of how do you actually represent this large 3D space without necessarily going first and building a gigantic map of it? And so if you're making a company, building a map of Paris as a first step is actually a very sensible approach. But if you're a biological organism, like you visit a city and your goal for tourism is to first build a map, this is crazy. And so this is sort of why I got interested in navigation. And to give you a practical example of how you can actually, what's an actual concrete problem we can do in this space, I'm going to talk about a sort of something which actually happened, and this is sort of the most tasty version of sort of slide preparation I've done. And so when I went to Paris, my postdoc advisor, Alyosha Efros, he's a bon vivant, so he said, okay, you have to go to this place called Blé-Sucré. And why do you go to Blé-Sucré? Well, Alyosha's like, okay, fine, there's this lemon tart. Now, these things are actually very difficult to find in the States because basically they're not sweet, they're really delicious, and they're wonderful. And so Alyosha's like, you have to go, you have to go. And of course, your advisor tells you to go, and so you have to go. So how do you go to Blé-Sucré? So I started out at INRIA, and so in fact, if you go to Paris, let me know. I'll give you advice about how to get to Blé-Sucré. And so you start out, you leave the building, and you head onto the main street. You go past this restaurant, you keep on walking, you get to like this sort of intersection. You take a right, you go to this thing. So there's this bakery here. You don't go here. This is okay for every day. You wouldn't walk here that far. You keep on walking, and eventually you get to this street. And then you get to Blé-Sucré, you get your tart, and then you're very happy. So you're able to do this, and suppose you can do this by, for example, pulling out your phone. Or if Alyosha sits down and writes down a bunch of directions, you can follow those directions. Now you've gotten to Blé-Sucré, you've gotten your tart. Now, you can ask two questions. Like, first of all, how do I get back? So I can't just go to Paris and eat tarts. That's just not, you have to do work. You have to somehow write papers. So somehow I have to get back to the lab. And so how do I do that? And the second question is, like, if I really like the tart, how do I repeat this? So I have a single demonstration, maybe done with my phone. Maybe Alyosha takes me. I have some demonstration of this path. How do I follow it in reverse, and how do I follow it again? And so this is actually a fairly simple thing that you do every day. So if you go to a new friend's house, and they show you to the bathroom, they're not going to be like, oh, I have to show you all the way back to the living room, otherwise you can get lost and end up like in my basement or on the roof or something. This is just basic human behavior. And if you actually sit and think about it, it's actually amazing you're able to do this. And the reason is because there are two big challenges. First of all, you don't actually precisely replicate your actions. And I know in a place that does robotics, I don't have to say this. This is like the big challenge of robotics. You don't actually replicate your actions. And it's not just robots. Humans don't. So in the psych department, you can do crazy things like you ask people to walk some distance while blindfolded and then walk it back. And so there's wonderful studies of how people actually walk around, and you can plot how far they are supposed to go and how far they actually go. So that basically, you walk one distance, and then I have to walk back. And if you have one-to-one correspondence, essentially you can actually replicate your actions. You get this nice dotted line. Now, if you notice a scatter plot, you don't get this nice dotted line. You actually get some sort of systematic under and overestimate. And on the right is actually going to be if you have turns involved. And people systematically screw this up. People don't do this at all. And so somehow you have to be able to replicate your actions even though you can't replicate your actions. So this is where vision comes in. So you have to be able to keep track of how far you've moved. Now, the problem, though, is if you look at vision, well, the world is constantly changing. So here's actually when I went to go to Blé-Sucré, there's this nice street market and there's tons of stuff. This is a wonderful landmark. If I need to find the street again, this is great. So if I'm just walking back, this is a great idea of how do I get back to the previous street I was on. This is very distinctive. Now, if I go back at 8 p.m., though, well, it's gone. And so the world, if you're actually dealing with the real world, things change all the time. And so the most informative stuff, like the cars, the people, the hustle, the bustle, this actually disappears. All the landmarks will disappear. And in fact, how you recognize a street is, or at least for me, is a sign which is not even visible to many of you, for example, in the back. There's a little sign in a restaurant, and that's how I recognize this particular street. And so you have to be able to go forwards and backwards with an inability to replicate your actions and with the idea that the world can change. And so this is a work that we did at NeurIPS 2018. The primary credit for getting this to actually work really should go to Ashish Kumar and Saurabh Gupta, who did more of the lion's share of the hard work of actually getting these systems to train and to work properly. And so I'm just going to be more specific and concrete about what the task is. I want to follow a path, either forwards or backwards, and I'm given a single demonstration of it, consisting of observations in the form of images and actions. So basically, I take this path, I see where I went, and I know what actions I took. And I specifically want to do this with a noisy actuation model, so I don't precisely replicate my actions. And the world can change while I'm doing things. And so this is a specific challenge. Now, of course, there are lots of ways to solve this, and we're not the first to tackle these sorts of things. There's a gigantic body of literature on this. And the two sorts of ways you can approach it is the very classic way to do it, which is going to be, okay, if this advances. Let's see, this is not advancing, okay. Aha, PowerPoint is not responding, all right. Give me 1 second. And so basically, I'll talk as PowerPoint is freaking out. The two ways you could do this is you could do the very classic way, which is you build a system with something like SLAM. And then what you're going to do is, in fact, there's a nice video, which is probably causing it to crash, of building a nice 3D representation of the system, and then you can then plan on top of this. And of course, this is great, but one of the big issues is that you're going to basically build the map independently of doing planning on top. And so planning and map building occur separately. So I'm not actually going to show that slide because apparently it's causing PowerPoint to crash. Okay, so we're not trying to replace classic methods. We're trying to, I think they're classic methods, and let's see. Classic methods are there are a lot of insights we can borrow from them, but classic methods, basically you build the map independently and you plan independently. And these two things don't actually ever talk to each other. And I think learning gives you an opportunity to match these two things up. The second way you can do this, which is very popular now, is end-to-end learning. And so you can basically drop some agent in a video game and you let them run around. And this is there's tons and tons of work here. Now, the difference for our approach compared to a lot of the end-to-end learning systems is that we're going to try to do this with one demonstration, so we don't get to explore the environment a million iterations. We're going to have noisy actuation, which turns out to be actually fairly rare in the end-to-end learning setups. Many people don't have noise, which is a bit terrifying. And we're going to let the environments change. So basically, we're going to try to make this more realistic and more challenging. And to be concrete about the agent we can control for this task, we're going to have an agent which can move forward, and it can rotate left and right 30 degrees. And so if we have this agent that can just do these 3 actions, there's a very big issue with this, because there's a very simple baseline of following a path again that works 100% of the time if there's no noise. So can anyone think of this? Like the dumbest thing possible, like something that a first-year computer science student might think of. If I want to follow a path again.
Big word strategy.
What's the big word strategy?
The famous song, want to go back with the first thing last.
Okay, that works exactly, yeah. For going backwards, you just make the first thing last. And so for going backwards, it works 100% of the time. Going forwards, you just repeat it. Exactly, so you just do this. You just replay your actions. And so if you don't have noise, you have these open loop policies just like will basically work 100% of the time. And so we're specifically trying a setup where these things will not work, essentially. And we'll show empirically that they don't work. So instead, the noise that the systems can control, you basically can, when you go forward, you rotate a little bit, so you have some noise, and then you move forward, and the going forward has a bit of noise too. And turning left has noise, turning right has noise, so on and so forth. And so you're going to be trying to control this sort of, think of it as you're trying to control an agent that doesn't really want to cooperate so much. And in reality, this is just that the agent it's noisy actuation. So how do we actually tackle this idea? We've given a single demonstration, and we're going to try to follow it. The idea is that we're going to try to generate some sort of abstraction, and then we're going to try to follow that abstraction. So we have a set of observations consisting of images and actions. We're going to try to generate some sort of abstraction that a neural network will like. So images and actions, these are high dimensional and not so nice to deal with, so we're going to try to pre-process it so that the network will be happy with it. And once we have an abstraction of this path, then we're going to have some sort of recurrent follower agent that essentially looks at the abstraction and tries to figure out, given if I look out the camera, given what I can see, can I then predict the action I'm going to take? So essentially, you're trying to generate an abstraction. So those of you who are from the pre-GPS era, you can imagine this as we're trying to create the map that you would print out from Google Maps, consisting of like the landmarks and sort of what turn you take where, so the 20-step map. And we're going to then have a follower that then looks at this map and then tries to figure out what to do, given that it's just looking out at the world. So how do we actually do this? So the idea is that we have this collection of steps of a path. And they consist of an image and then some sort of action, like, for example, this image and then turn left. And the image is, of course, 256 by 256 by 3 or something. This is lots of dimensions to work with. So we pass it through a convolutional neural network that we're going to train. This entire thing, by the way, is end-to-end trainable. And so we then pass this through a network, and this gives us a feature vector. And so this feature vector is just some lower dimensional representation. And then we have an action, and you can represent this as like a one-hot encoding. And together, you take the image, convert it into a feature vector, and the one-hot encoding, and this is just some vector which represents what we're going to call the memory. And so you can think of this as I take your entire path, and I convert it into some sort of vector memory that represents what I did and what I could see at this location. Now, if I do this for all the steps of the path, I get a series of memories. And so these memories are going to be the demonstration of the path that we get, and we're going to try to basically recreate what happened given control of a noisy robot just by looking at these memories. And so to do that, we're going to then, rather than dealing with the images, we deal with this memory. And we're going to try to plug these memories into a recurrent model that systematically just looks at the world through the camera and then spits out an action to take. And so you can think of this, the sort of analogy to have in your head is this is kind of like some sort of very weird translation module, where instead of translating from French to English, you're translating from your memories to essentially the actions you perform. So it's going to be like an LSTM or any of these recurrent models, where you're essentially looking at inputs, which are the memories you have, and then producing actions as outputs. So essentially, it's a translation system. Now, specifically, we're going to use a gated recurrent unit. You can, if you know what this is, basically these tended to work better than LSTMs for a particular task. And so what we're going to do is we're going to sort of, at every time step of this procedure, so it's a recurrent network, so it sort of goes through a series of sort of time steps. We're going to look at the memory. And rather than looking at all the memories all at once, we're going to pay attention to a specific location. We're going to have some sort of pointer. So you can think of this as the step at which you are in sort of your navigation procedure. So this will keep track of how far we are in terms of tracing this path back. And we're going to then take this pointer, and it defines weights over the memories. And then what this lets us do is we can then take a weighted combination of our memories, and we're going to call this mu_t. And so this represents what we saw and did at this approximately this location. And this is all learned end-to-end, so you can basically generate feature vectors which can be averaged like this. So this gets plugged into the recurrent module. And then we're going to have, these recurrent modules have states, and so we're going to plug in the state as well. And then we're going to plug in the observation. So essentially the observation comes in, you're looking at where you are in your memory, and you're looking at your current state. And then from that, we're going to then produce the action. And then we're also going to update where we're looking in the memory. So essentially at every single time step, we're going to sort of be producing the action as well as the updates to the state of the system. And of course, because this is a recurrent model, we also have to produce the update to the hidden state of this model. So essentially, you can think of that every single time step, you're just taking a look out the window through the camera, choosing to do something, and then updating the sort of internal parameters of your system. And the important thing is that we're actually only interacting with the world through an image and through producing actions. So we don't actually get any sense, we don't have like a GPS system on this robot, essentially. So we only know the image and the actions, essentially, that we've taken. Yeah?
How different is the new versus your image observation data?
So you can think of this as taking an average of the image observations, but it's doing it in a space which is where taking averages makes sense. Yeah. And so this is all end-to-end trainable. So if you basically, this entire system, there can be a bunch of arrows and everything. Think of all these arrows as just simple functions that have parameters, and we can train this so that you can figure out how to represent your images so that they can be averaged and used as input like this. So this is a forward pass, essentially. And to get to the next step, we have our outputs, which is the action. So this gets sent to the simulator. The update to where we're looking, and the update to the next step. So the next state, essentially, you just update this. And then to update where you're looking, you essentially just pass it through a sigmoid. So you can essentially just say, you can think of it as I have my finger on my map, and I figure out how far to move my finger up. So basically, I just move it up. Maybe if I think I should go to the next step, I just move it up by 1. If I think I should stay at the current step, I stay at 0, essentially. And so this is essentially just converting these observations into actions you would take. And so you can train this on a series of sort of run-throughs of basically trying to follow a demonstration of a path. And so specifically, we train it with a bunch of reference trajectories, which are 30 steps. So we generate these with just sort of classic search. You just have a bunch of reference trajectories. And then we train it by imitation learning. And so we have 120,000 episodes of where the system essentially gets to produce 40 actions as outputs. And it tries to basically get as close as possible to the goal that was demonstrated to it. And the reason why you have 40 steps is because if you have noise, you can't actually get there in 30 steps all the time. And we do it by imitation learning. So we have access to a simulator so we can figure out which steps actually take us closer to the goal. And so we can actually sort of train this by imitation learning quite nicely. And of course, this depends on a simulator. So there's an open question of how you would transfer this to a real robot where you can't necessarily generate this type of supervision. And then the networks we have are fairly simple. It's like sort of 5-layer CNNs for processing images, and there are a whole pile of multi-layer perceptrons floating around in the middle.
So just be clear, so the reference is only one reference or multiple references?
You get one each episode you get a single reference. So you can think of this as like meta-learning, where you get each episode is one demonstration, but the system is trained on multiple demonstrations. So like in translating sentences, each time you get a single sentence, but when you're training, you train on lots and lots and lots of sentences. Yeah?
Well, does the simulator know about the setting or the environment?
The simulator knows everything. So this is one of the limitations right now. So it's not clear how to translate this directly to real settings. We have had some success taking this and running it off the shelf in fairly simple environments. But the simulator knows everything, which is why we can do this with imitation learning. So if we had a real world, we might have to do something like, we might need to do reinforcement learning with reward shaping.
Does the simulator have a really good render, or is that not crucial?
The render is not crucial. We tried on two things. I'll show you hold that thought, and if I don't answer it, bug me. Any other questions? Okay, cool. One thing, though, I want to point out is that because this is all trained, you can actually do a couple of cool things. So for example, if I'm returning home, if I'm trying to get this to basically go to Blaise Sucre and then come backwards, when I'm returning, the images look different. So I'm seeing things from a totally different angle. And the cool thing about this entire setup is because you can essentially give it a demonstration and then you ask it to then follow this path and return home, you can actually just stick in a bunch of extra layers in here, and you can actually train the features so that they work when you are trying to go in reverse. And so essentially what you can do is you can then have a learn function, which essentially you just stick this in as a bunch of extra layers inside your network, which will flip the images for you and essentially try to imagine what it will look like. Essentially, you can think of it as trying to produce an image representation which will be usable even if you're going backwards. And so we can actually train this thing to work in reverse as well. And this is just simply by doing it with just adding extra layers. And so of course there are ways to do this with standard classic techniques, but here we're just going to train it. Oh, yeah?
Do you have any idea, if you looked at the features, the embeddings on this memory, whether it is egocentric or like God's eye view?
That's a good question. My impression is the features are probably not very smart, actually. I think it probably does not learn to map very well. It probably learns, we don't have a good idea, but I would say that this current setup does not do a lot of the type of behavior you'd expect from sort of a God's eye view type thing.
I'm asking because Sora has in the
Yeah, in the previous.
At some point it looked like it.
So Saurabh's earlier work, you actually have a representation which you can accumulate because you're going around in space, and you know how far you moved.
He had an allocentric representation.
Yeah, you had an allocentric. Yeah. But the catch is that in this sort of follow-up work, we don't have this representation. You can't necessarily accumulate that because if you have noise, you don't know where you are specifically. So you can't accumulate it in that way. Yeah. Okay. Cool. So in terms of evaluation, we evaluate on two different environments. So one of them is going to be the one that you probably saw when Saurabh was here. And that's going to be the Stanford building data set. And again, by the way, we're always testing on held out data. we train on one set of environments and we test on totally different environments, because otherwise this is nonsense. The other thing that we do is that we test on SunCG, which is basically, it has a very terrible render. So you can see that this is awful, like this is awful graphics. And so the reason why we train and test on this is because we can then insert and remove objects without the network noticing. So you can, because it's a render, you can just add things or remove things, and it's totally fine, and it's totally normal. And so again, we test on held out data here. So we're not training and testing the same environment. Okay, so we do some experiments. The baselines we have, the first thing that we do is open loop. So we just replay the actions, either forwards or backwards. And so this should not work if we have challenging data. A lot of people don't test against this. This other thing that we do is visual servoing. So this is just a classic way to try to get to from one place to another. And so we have some implementation of this. And we also have a classic method, which is using ColMap, which is like an off-the-shelf, state-of-the-art reconstruction-based technique. So we reconstruct, we figure out where we are in that reconstruction at test time, and then we execute the ground truth best action. Now, one thing I want to point out is that what this entire field is missing is very good comparisons between more classic techniques and these learned techniques. So I'm not claiming that this classic method of ColMap is like the best way to do this. What I think this field needs is someone who does classic techniques to actually try on these benchmarks and maybe beat all the learned stuff, which would be very exciting. But I think we're missing the real comparison between these learned techniques and classic techniques.
But in the tasks you showed, following back, if you use Google Tango, there is no way to achieve the performance of Tango or from Quadratos, CJ, or anything. I mean, the established techniques are very hard to.
They're very hard to beat, but
actually they might be boring.
But there's so we tried. So okay, if you have a single path demonstration, though, what we found is that the reconstruction techniques, depending on what you have access to, like an image, if you have just an image, we found that the reconstructions, obviously, if you can get like nice loop closures and wander around for a while, then you can't beat this. I would agree. If you're training and testing on the same day, but if you have a single path demonstration through a building, you might have issues, I think. We had issues trying to reconstruct stuff, actually. We found that in practice with very untextured environments, this is quite difficult to get this stuff to work perfectly. But this is an area where it's crying for someone to do this experiment, and there are lots of challenges where you can just beat the pants off of people. Yeah?
I hear you suggest that in the boring hallways where there aren't very many features, that your scene-based action sequence memories will be more effective in classical. Is that the suggestion?
That would be the suggestion, that in very boring tech.
Could you motivate that? Because it seems that you put a lot of stock in the place-centric representation of progress, right? And so if the places are easily usable, the perceptual equivalence classes are multiple.
Yeah. So
This is gonna
sure. So in the case of going down a textureless hallway, if I try to reconstruct this, you're going to have a bad time, which is why you often see lots. But the strategy you can do is if you're just going down a textureless hallway, or like going down a highway, for example, for miles and miles, you say, okay, I will continue to do this until I find this door. You can essentially say, okay, I might be lost. I don't know where I am in the hallway, but I know I just have to follow this hallway. And so in principle, you can learn to do that.
So the path length will go up in your system, is that?
The path length will go up.
In other words, as the confusability, as the perceptual equivalence classes get more multiple, then your path length of execution will go up.
Not necessarily, in the sense that if I walk down a textureless hallway, I don't necessarily know where along the hallway I am. But I can say, okay, I can just keep on following this hallway until I reach the end. But if I try to reconstruct, I might have issues.
I mean, the key is on looking on the ground. The ground really has a lot of features, and it's really, I mean, these guys have done, first they use a very good IMUs, which are better than the FNX copy you're using here, the action. And then there is a lot of engineering on outliers and answers.
Sure. So I mean, there's a lot of engineering, and I think okay. I'm not saying that the learned system is here to replace these systems. I'm saying that there is an ability to navigate in environments that is certainly, like in the case of humans, it's certainly learned. They certainly don't look at swift key points on the ground. People do not look, I can obviously recognize this texture. I could probably recognize this carpet compared to other carpets by looking at, looking very carefully. But humans don't seem to do that. Organisms don't seem to do that. Like mice don't seem to do that. So I think there is obviously in organisms, there's some amount of learningness which is going on. And I think.
Sorry, lots of organisms in a different environment that do exactly what this is very much on the environment.
Sure, there are lots of strategies.
Very dangerous statements to make.
I guess what I'm not saying that the organisms don't do that. I'm saying that there are certainly going to be ways in which, like, I don't certainly recognize the SIF key points on this ground. Like, I couldn't be forced to ask, like, where I am on this carpet based on this.
You use the
Yeah.
You use the optical slope for path integration, and that's proven for all animals.
Sure. Yeah, you do. I guess what I'm saying is, one thing what I will conclude with is, I think this is the learned navigation type stuff is an alternate way of doing things. There is some degree of learning involved. I think what's interesting about these discussions is there is a lack of communication between these two fields, and I think there's also a lack of comparisons, and it has to do with what systems are available. And I think what would be very interesting, and as a person who's very interested in 3D, I think what would be very nice is if the fields can connect together and people can actually do comparisons. So we compare it against this sort of stuff. A lot of people don't, and I think what is missing is that there are these two areas that do not talk to each other and should actually talk to each other more and compare more. And so it's more of an open invitation.
Hey, I like your approach a lot. But I had a question. Maybe this is sort of towards the end. In what you're doing, it seems like there's sort of two very important questions. One is a question of representation. The other question is action. And sometimes they get confounded.
Yeah.
You're thinking of this as a process that goes from image all the way to action. And I'm wondering in your mind if you sort of see those as sort of two separate things. And that I think there's a very strong argument that you made very well as to why you would want to have different ways of thinking about place and recognizing that. Which actually is not the same as deciding what it is that you want to do. Because one day you want to go to the bathroom, the next day you want to go to the ballroom. These are.
Yeah, they should be separate. So right now, because in this particular setup where you have simply observations to then trying to produce actions, they are being confounded. I think the bigger question is how do you represent large, much larger spaces where you can't necessarily do path integration over long, how would you represent sort of like if I have Paris and maybe I have sort of like a graph type representation. Yeah. Okay, but I'm just gonna plunge forward. So I'll actually do some. I will show. Okay, I'll just do running it backwards. So you can sort of walk out here is the system running. You're just going to walk out the door, and then we're going to sort of follow the path in reverse. Now, so in terms of comparisons, obviously what we're doing is we compare against open loop, and open loop doesn't work very well. So specifically because it has to, it's obviously not looking at the image, and so it doesn't actually, if you have noise, it doesn't actually sort of compensate for that, and so it can just bump into walls essentially. And so here we have the system running in reverse. And by the way, you can train a system to, not train a system, you can design systems to have descriptors that work from very different angles. You can reconstruct things. What I want to point out is that you could imagine the system is able to, you can either design systems that can work in reverse, or you can provide training data so that the systems are forced to work in reverse. I think there are two different design philosophies. And I think there has to be more communication about, there are lots of strategies that we can learn from how you engineer these things, but I think the idea of designing these things by providing the data is also a very valuable approach. And so, here's a proposed, okay. So I'm just gonna then show some results. Of course, open loop doesn't work. The classic method gets very close to our results. And I think again, as an advertisement, these types of navigation things, I think it would be great if people can compare more. And it would be amazing if a classic technique would beat all the learned systems, and that would be great. And I'd love to see that. Because that will then provide us with useful information about where the systems fail and where they succeed. And that might provide a much better sense of how these things work. Okay, so going in reverse, open loop works the same because it's just by symmetry. And the classic technique, of course, doesn't work at all because we're simply reconstructing from a single forward sequence. Of course, if you navigate around and do loop closures, build a beautiful 3D model, this is quite useful. And you could imagine doing that. But here we're doing a single demonstration, and trying to imagine these things from a different angle is going to be quite difficult. And so you don't, basically your system will get lost very, very quickly, simply because it's trying to basically go down the hallway from a totally different angle. So SIF descriptors don't really work. And again, you can engineer your way out of this, but you're going to be, that's an engineering solution as opposed to perhaps a learning solution. And the two are different, valuable. I'm not going to show you the changing world thing, but you can imagine that if I add and remove furniture, if I just follow the open loop thing, it's going to have difficulties. And if I reconstruct things, if I add stuff or change things, all of a sudden it becomes difficult to localize because the objects have moved, or something has been added, or something has changed. And so it's very difficult to figure out where you are. So I'm just going to flip to the numbers. And so on the x-axis is the number of objects we have as a function of at execution time. So on the left is going to be fewer objects. On the right is going to be more objects. And our system, because it's trained to sort of, it's sort of entirely learned, and can essentially learn to sort of not bump into things, or can learn which things are useful for localizing, can actually do fairly consistently as a function of how many objects there are. Now, if I just do open loop, as I add more objects, I bump into things more. And so I succeed fewer.
In this graph, the training was at what?
Training is at 100% in the middle. So you just remove objects or add objects. So the open loop is going to basically do worse. And then classic 3D, which is again this coal map thing, is going to do worse as you add or remove objects because localization gets harder. And so this is going to be, obviously you can say, okay, fine, we don't have SIF key points on beds. And there's lots of work where you say we remove SIF key points from cars, we remove SIF key points from trees. But here, we're not designing the thing, we're just letting the system learn. And in conclusion, one bit of closing thoughts, and I'd love to continue these discussions offline as well. If you do forwards and reverse, obviously the classic method doesn't work in reverse, and there are obviously engineering solutions for this. Same thing, if I change the number of objects, there are obviously engineering solutions for this. I think the difference in this approach is that you can design solutions to problems, or you can design data to solve the problem. You can essentially provide challenges that it has to be able to solve. And I think the two are complementary types of approaches.
What do you mean that they reverse? What do you mean that they reverse? You cannot follow the same path?
Basically, when you reconstruct it, you can't localize yourself. If you localize yourself poorly once or twice, then you end up,
I'm sorry to say that, but CG has a system which flies 1 kilometer into the woods for the first time, and comes back in a distance of 1 foot in a dark lake.
So what I said is, when I introduced CoalMap, I said specifically I'm not claiming that this is exactly the system. I mean, the issue is that CoalMap is the best available system that is openly available and sort of for which for SIF-based reconstruction. I agree that there are perhaps better systems. We tried a bunch of stuff. CoalMap was the thing that we could get our hands at worked the best. So the system, does it have an IMU? I mean, this is probably better done offline. I'm not saying that you can't go backwards using SIFT. I'm saying that if you use CoalMap, you can't necessarily localize yourself going backwards. Now, of course, you can design the system to work better when you're viewing from a different angle. People have been doing ASIFT for ages, for example. I'm just saying that you can also learn this. Okay. So far I talked about how you can get here and backwards. And so I want to then talk very briefly in the remaining time about how we can understand sort of opening and closing objects, or sort of interacting with system objects. So I got interested in the idea that if I want to understand how this, basically how this scene can be interacted with, we can simply watch the person interact with it. And so the idea that I have had for a while that I've been interested in is trying to learn about how the world works simply by observing basically people interacting with things. Now, the standard approach to getting this sort of data turns out to be, in computer vision, the way you collect data is you're very explicit about it. And so if I want to understand everyday interactions, I can make a list of things to do. For example, you get out of bed, you brush your teeth, And so you can basically collect data this way. And the problem is that when you try to get interactions with objects, so for example, opening a laptop, if you search YouTube for this, you actually find lots of very bad stuff. So you find people opening laptops to replace the RAM. And so if you do this for things like opening refrigerators and all this other stuff, you actually can't, you basically can't get data this way. And so if we're going to train robotic systems that interact with the world, I think if we want to have these things work on diverse data and learn from diverse data, we have to have better ways of collecting this data, essentially. So searching for YouTube, which is a standard computer vision technique, doesn't actually work on this simply because nobody is going to tag things. So if you expect, anyone who basically videotapes this and uploads it to YouTube and says, this is me opening a laptop, basically they have bad hobbies. Now, if you expect this to actually exist on YouTube, tagged as opening a laptop, you basically need a reality check. And so one thing I've been working on has been collecting large amounts of interaction data from YouTube. And so this data is basically very difficult to get at scale because people don't tag the data, essentially. No one's going to say, OK, here's a video of me cutting a watermelon. And so we have a data set called vlog. It's like 114,000 clips. It's 14 days of footage of people doing really boring stuff. In fact, another area where I think I'm hoping to find an interface with robotics and where robotics and computer vision don't really talk enough is in terms of the sort of data of interacting with objects. And I think there's a nice interface of trying to learn from these types of YouTube videos, and this sort of YouTube videos can provide an extra source of additional information. And so in general, one thing that I can talk about this offline is you can find these really boring interactions if you know how to look. And we have ways of doing this. And we're trying to basically apply this more broadly. But if we gather data this way, so we can gather lots and lots of YouTube videos of people opening things and closing things and doing everyday stuff, the big challenge is that once we get the videos, you still need the supervision. So I can, if I have a bunch of videos of people doing stuff, I don't necessarily know what's going on in those videos. I have videos of people's everyday lives, but I don't actually know what's actually happening. Now, realistic data also has basically way too many nouns. So if you look at the types of data that you find on the internet, you basically have a very, very long tail. And so you don't have thousands of demonstrations on a single object. You don't have thousands of demonstrations on a single category. You actually have, realistically, each object you see very few demonstrations of if you have realistic data. Now, one thing I'm going to talk about briefly is the idea of using instructional videos for training. And so the idea that I think is exciting is you can find on YouTube videos that come with the weak labels intrinsically. So rather than getting a mechanical Turker to label things, you can actually just get data that comes pre-labeled. The second thing is that I'm going to talk about briefly sharing basically concepts between tasks. So I'm going to show you how you can sort of compose classifiers from sort of base concepts. So this is work on instructional videos. All these people, so Dmitry Zukov had to deal with 5 people telling him what to do and get stuff to work. So he gets a tremendous amount of credit for this. All right, so I'm going to show you briefly one of these videos so you get the sense of what they look like. So here we have a YouTube video. We'll play. All right. All right, videos are not playing today, which is very surprising. Okay, all right, so sorry about this. These slides worked last time. Something about maybe the projector. All right, so if you watch this video, what would happen is that basically the person is talking about making pancakes. And so people record themselves doing things like making pancakes. And as they do things, in the same way, if someone is demonstrating a task for you, they're going to talk about what they actually, what they're doing as they're going on. And so, we're going to get videos which consist of people telling what they're doing when they're doing it. They're also going to mention what other things that they're going to do in the future and the past, so it's not exactly noisy or not exactly clean data. And so we're going to start with a list of steps for a given task. So we know approximately what making pancakes, for example, looks like, or making meringues. So the meringues consist of like pouring eggs, whisking mixtures, and a whole bunch of other things. But we don't have a list of steps per video. So we just know the general idea of what we're trying to do. And we're going to have a narrated video. And the narrations are going to consist, it's just what people naturally say. And the interesting thing is that you can use this as supervision. Now, the key thing that makes this work is that we're going to do this for multiple tasks simultaneously. So we're going to not only learn about making meringues, we're going to learn about making pancakes and making lemonade and making all sorts of other things. And so in general, this is a sort of setup where we have a list of tasks, or a list of steps in a task, and we have narrated videos. And we have multiple tasks that we're learning simultaneously. And we can use this these narrations as a cue along with a list of steps of tasks in order to figure out what's going on in each step of the video. And again, something like, for example, pouring will happen in multiple locations. And we can use that as essentially supervision. OK, so the method, I'm just going to go briefly. We have a list of shared components. We basically break up the list of steps that we get. And these come from essentially a website called WikiHow, which contains lots of very interesting instructions for how to do lots of weird things, but also lots of normal things. And so we just have a list of things like mixture, milk, pour, egg, whisk, spread. And then we have a bunch of tasks. And the tasks, like making pancakes, there's pouring milk. Making meringue, there's pouring egg. And so the pour appears in both of these. And so we're going to have a classifier for pour milk, which consists of a classifier for pour and a classifier for milk. And we're going to combine them to make a step classifier. And this classifier, we're just going to add up the scores. And of course, this is a very big area of computer vision of how you do compositional stuff. And there are much smarter ways of doing it. We're just going to do the most basic thing. And this will get us into trouble later, but it works effectively for many things. And so you can just add up the pouring milk is just pouring, and the milk classifier combined together. And so our goal is to learn classifiers for all these components all together. And the way that the method works is we have essentially a narrated video and a list of steps for each task, but not for each video. And we want to have a labeling of what happens where in the videos and a classifier that will recognize, for example, when pouring happens or when there's milk in the scene. And essentially, this is a totally unconstrained problem. So essentially, if we just try to find the labels of the videos and we try to find the classifiers, if we just dump in a bunch of data, nothing's going to happen because we need some sorts of constraints. And I'm just going to skip over a tiny bit of the math. And I'm just going to talk about we have an alternating method. And the key is that we can apply constraints at the right place and then basically make this problem actually have traction. And basically, we're going to alternate between learning the why, which is what happens where, and learning the classifiers for what happens, basically a detector for like pouring actions and for when milk occurs. If I have a bunch of labels, it's going to be basically a supervised problem. So I can just train a classifier off the shelf. So we train standard, we just have a linear model. It turns out we don't have a lot of data for any individual task. So we have lots of data, but it's all divided out among lots and lots of tasks. So we just do supervised learning. If I give you the labels, you can train a classifier. The interesting thing is if I have the classifiers, how do I get the labels? And how does this actually process start? Because if I just say, oh, we dump in data and we get classifiers automatically, you should say, I should be skeptical of this. This is not going to work because it's essentially it's not constrained enough. And so if I take the classifiers, I can get a probability of each thing occurring at each frame. So for example, when does pouring happen? I have a probability distribution over that. And I can take the constraints I can basically generate constraints from the narrations, which tell me that if I mention pouring, it's likely that pouring is occurring here. And I can also add constraints in terms of the order in which things occur, and I can ensure that each thing occurs at least once. And so these constraints are actually noisy in the sense that sometimes people leave out steps, sometimes people do things in the wrong order, but they provide us with enough traction to actually learn what, for example, pouring looks like. So we have a new data set. I'll skip over this. OK, so I'm just going to show you some results testing on unseen data. So here we have the task of building shelves, and we can learn to predict what cutting shelves look like, what assembling shelves, and sanding, and this sort of stuff. We also test on tasks like making food. So it's not perfect. Like peel banana on the left is not great. But we also things like cutting, which have distinct emotions, we do pretty well on. If you're looking for another area to work on, this data, there's lots of room to grow. Our current setup, we just combine classifiers by adding them. This is subpar. And so if it sees, for example, things like whisking mixture, if it sees a whisk, then it just says, OK, this is definitely a whisk mixture step, even though actually the person is pouring here. Same thing with lemon. So anytime it sees a lemon, the lemon classifier is really easy because you just look for something big and yellow. And so anytime it sees lemon, it sort of detects, says cut lemon is here, even though there's no cutting involved. Squeeze lemon is here, even though there's no lemon involved. Essentially, the noun classifiers can overpower things. So I think what's interesting is that there's a lot of work to be done in terms of how do you combine these classifiers.